Hello everyone and welcome back to Diksha Karnataka YouTube channel, and you are watching KCET 60 out of 60 in physics series where we are discussing each and every chapter concept wise. So today we are going to discuss magnetism and matter, and in this part we are going to discuss about bar magnet, solenoid and Gauss's law. In the part 2 we will complete this chapter. This is a small chapter, so everything will be completed within 2 parts. Now from this chapter we generally get 2 questions every year. I will show all the previous year questions as well when this chapter is over. Also, if you want to get all the latest update whenever we are doing an upload, you can join our WhatsApp channel. The link will be given in the description. Also, the lecture notes, lecture PDF will be available in the comment below. You can download all the lecture notes from the comment below. Now let's start with the part 1. What all we are going to cover in this part? First of all, we are going to cover bar magnet, then we will cover magnetic field lines, then we will cover bar magnet as an equivalent of solenoid, then electrostatic analog, that is basically comparison between magnetism and electrostatic equations. Then we will also cover magnetism and Gauss's law, so basically the Gauss's law of magnetism, right? Let's start with the first part, bar magnet. So this is basically introduction to the chapter. Earth behaves as a magnet with the magnetic field pointing approximately the geographic north and geographic south. In reality it is not exactly at the north or south. Okay, if you see the earth, if you draw the earth, this is the north pole, geographic north pole, this is geographic south pole, right? But in reality the magnetic north pole will slightly bent like this. Okay, this is magnetic south, you can say this is magnetic south, this is magnetic north, and this orientation changes with each passing year. After certain amount of time this rotates. Okay, now but the rotation is very slow. Also, you should remember that when you hang a magnet, suppose you have a magnet and if you hang it, okay, it will automatically point towards the north pole and south pole, whatever. Suppose I am assuming that these two points are coinciding, so that there is no magnetic north pole and magnetic south pole are actually almost on the geographic north pole and geographic south pole. Now if you hang a magnet will point, one end will always point towards north, and I will call that pole as north pole, and whatever side is pointing towards south is called south pole. Okay, so each magnet has 2 poles, okay, north pole and south pole. Now next, move on. There is a repulsive force when north poles or south poles of 2 magnets are brought close together. So what is the meaning of that? So if I brought 2 north poles of one magnet and one north pole of one magnet and another north pole of another magnet, okay, there is a south pole there somewhere, I'm not showing that, so this will repel each other. Similarly, if I brought south pole of one magnet and south pole of another magnet, they will also repel each other. These are easy things to remember. But if I brought, say, north pole of one magnet and south pole of another magnet, okay, they will attract each other. Okay, similar to that of electrostatic charges, where we have seen positive charges, 2 positive charges repel each other, 2 negative charges repel each other, but a positive and a negative charge attract each other. Similarly, here also we can see the north pole repel each other, south pole repel each other, but north and south attract each other. Okay, now let's move on to the next point. We cannot isolate the north or south pole of a magnet. Very important line. We cannot isolate the north or south pole of a magnet. What is the meaning of that? For example, I am just giving one example. We have studied in electrostatics, we can separate positive and negative charges, right? Even we have charged using fur, wool, rubber, etc. We have separated the different charges, but in case of magnetic poles we cannot separate them. Okay, so for example, even if we have a north south pole, okay, you might think, okay, if I break it from here, okay, I make 2 separate poles. That is not possible. As soon as you break it, here a new south pole will appear and here a new north pole will appear. So magnetic monopole, it is called magnetic monopole, ideal thing, okay, imaginary thing which cannot exist in nature. Magnetic monopole cannot exist in nature. Magnetic monopole means only north. or only south. That is not possible in nature. If a bar magnet is broken into two halves, we get two similar bar magnets with somewhat weaker properties. Okay, obviously if I break this magnet into two halves, they will not as strong as previously, but they will reduce their attractive powers, but still they will behave as magnet. Okay, unlike electric charges, isolate magnetic north and south poles known as magnetic monopoles do not exist. Very, very important line. Magnetic monopoles do not exist in nature, right? It is possible to make magnets out of iron and its alloys. Okay, so iron, there are few metals that can be converted into magnets. Okay, we will study about that in the later half, part 2 of the chapter. Okay, there we will study about different types of magnetic materials. Okay, but iron is one of the most commonly used material which is converted into a magnet. Can you name one more material which is used in magnets? It is very common. It is available in toys. You can get it in your home. It's a very strong magnet. Tell me the name if you know that. Okay. Now bar magnet, when you take a bar magnet, okay, and if you put some iron filing means iron dust. Okay, if you collect some iron dust from some factory and if you pour, the bar magnet is below this paper. Okay, there is a paper kept it in here, then bar magnet is put on below that paper, and if you put the iron filings, they will arrange like this. Okay, the bar magnet will arrange the magnetic iron filings in this way. And can you tell me any similarity with anything that you have previously studied? Let's see what all we can infer from that. The pattern of the iron filings suggests that the magnet has two poles similar to the positive and negative charge of an electric dipole. Yes, in electric dipole, if you remember the electric field lines of an electric dipole, it similar to that. We have two poles. One pole is here, another pole is here. So basically you can say one positive charge, one negative charge. So to form dipole in electrostatics, okay, we have to have two equal and opposite charge, right? Two equal and opposite charge separated by a small distance. Magnets always appear as a dipole. Okay, and in this case the distance may not be does not need to be small. Okay, in this case distance can be as large as possible. Okay, for example, even our earth having north pole and south pole has a dipole moment, very weak, very weak, but still it has a dipole moment of its own, right? Now let's move on. One pole is designated the north pole and other is the south pole. Now from this diagram it is very difficult to identify which is north pole, which is south pole, but one of them is north pole, one of them is south pole. For convenience, let's say this is north pole and this is south pole. Okay, just for convenience, let us assume this is north pole, this is south pole. Okay. Now, when suspended freely, these poles point approximately towards the geographic north and south poles respectively. As I said, this will point towards geographic north, this will point towards geographic south, and that's how our first ancestors, very initial stages of the human civilization, we started to move from one country to another country using something called a compass. Compass is basically a magnet made from natural elements, and it points always towards north. So even if you lose your way, you can use that magnet to find your direction. Okay, also there are pole star etc., but magnet is also very common while navigating in the seas in the early years of human civilization. Now, a similar pattern of iron filings is observed around a current carrying solenoid. Another important line. So if you see similar pattern in a solenoid, so what you can conclude? This is observable on a bar magnet. Same thing is observable in a solenoid. So that means that you can consider a solenoid as a bar magnet. We will come back to that in a while, but let us look into the last week's homework problems that I gave in last Saturday. A galvanometer coil has a resistance of 50 ohm and the meter shows full scale deflection for a current 5 milliampere. If the galvanometer is converted into voltmeter of range 0 to 20 volt by connecting. So what is the main thing? The galvanometer coil has a resistance. So resistance of the galvanometer is given 50 ohm. Okay, and it shows a maximum deflection of 5 milliampere. So what is the maximum deflection, maximum current? Ig is 5 milliampere, that is 5 times 10 to the power of minus 3 amperes. Okay. Now when you convert a galvanometer into a voltmeter, what you have to do? You have to connect a resistance in series. Okay. So whatever the galvanometer resistance is, you have to connect an external resistance in series, so that the maximum current passing through the galvanometer is restricted to Ig. Maximum current restricted to Ig. Right. Now what else? It is given that we have to convert this into a 0 to 20 volt voltmeter, right? 0 to 20 volt voltmeter. Now 0 to 20 volt means when the voltage is 20 volt, okay, across the galvanometer, the current should be maximum current, that is 5 milliampere, right? For any other less value of voltage, current should be less than that, but at the maximum end, at the maximum value of voltage, Ig should be this, right? Now from Ohm's law we know that V equals to IR. Okay, now R is here Rg plus external resistance. They are connected in series, right? High value resistance connected in series. So the equivalent resistance will be Rg plus R. So we can write Rg plus R should be equals to V divided by Ig. What is V? V is 20 volts. Ig is 5 times 10 to the power of minus 3 equals to now 20. 10 to the power of 3 means 1000. It will go up and it will become 1000 divided by 5. 5 4s are 20. So Rg is 50 plus R equals to 4000, right? So R should be 3950, right? Don't ask me how this subtraction happened, right? If you don't know how to do this subtraction, you should go back and study in class 5 or class 6. Okay. Now let's look into all the options. The first option is 3950, but it is says parallel to the galvanometer, which is wrong. Parallel to the galvanometer is not correct. Series with the galvanometer. Series is the galvanometer is correct. As we know, to convert a galvanometer into a voltmeter, we have to connect high value resistance in series. So correct answer is option B. Be careful. Don't just look into the option and tick it. Okay, you have to check whatever else is given into the question. Right. Now let's move on. The number of turns in a coil of galvanometer is tripled. Okay, then both voltage and current sensitivity remains constant. Voltage sensitivity increases 3 times. Okay, let's see. So we know that current sensitivity NAB by K, right? So if you increase the number of turns to 3 times, so phi I dash will be 3N A B. Okay, A area and magnetic field remains constant, K is constant, so 3 phi I. So if you increase the number of turns 3 times, then the current sensitivity tripled, right? Now what is voltage sensitivity? Voltage sensitivity is NAB divided by RK. So resistance of the galvanometer will be incorporated in the voltage sensitivity. Now voltage sensitivity, now if you increase the number of turns to 3 times, okay, that means if there are say L length of the wire was there initially, now you are making it to 3L, right? 3L means the length is tripled. Now we know that resistance is directly proportional to the length of the wire. So you are increasing the length to 3 times. So the voltage sensitivity dash will become 3N. You have increased the N to 3 times, right? Number of turns to 3 times, length also becomes 3 times, so resistance also becomes 3 times. Okay, so they cancel, so that is basically equals to 5. So voltage sensitivity remains same, current sensitivity increases. So you cannot increase voltage sensitivity by increasing the number of turns, but you can increase the current sensitivity by increasing the number of turns. Okay, so the correct answer is voltage sensitivity remains constant and current sensitivity increases by 3 times. Okay, so this is the correct option. Be careful while answering such questions. Most of the people will answer voltage and current sensitivity remains constant. Some people will answer, some people will see, okay, both of them will increase 3 times. No. Okay, now let's move on. The magnetic field lines, very important concepts. Okay, as you can see, magnetic field lines of a magnet or a solenoid. Okay, now as I said that solenoid and magnets are basically one or the same, we will see in a while. Okay, but for solenoid or for magnet, both of them will show this property, form continuous closed loop. So whenever you are considering a magnetic field lines, they are basically closed loop. What is the meaning of closed loop? So if they start from here, they will end here. Okay, so they are closed loop. Now, unlike electric charges, in case of electric charges, if you remember, they start at positive, and if there are no other charges present, they will go up to infinity. There is no infinity business for magnets. Even if you see these are going towards infinity, and you might think, okay, they will reach infinity. No, after a long time they will come back somewhere and they will enter back. Okay, so basically they are closed, and outside the magnet they are traveling from north and going towards south, but inside the magnet it goes from south to north. We are coming to that in a while. Okay, so magnetic field lines are basically closed loops. Okay, shapes does not matter. Okay, shapes can vary, but they will always form closed loop. Okay, the tangent to the field line at a given point represents the direction of the net magnetic field B at that point. So if I find some magnetic field line, okay, and at any point if I draw a tangent, that tangent will represent the direction and magnitude of the magnetic field at that point. Okay, tangent basically represent the direction, magnitude you can find, and you can represent it using the length of the tangent. Now, larger the number of field lines crossing per unit area, the stronger the magnitude of the magnetic field B. So suppose I have a field, I have an area. Okay, in some case only one line is crossing this. So the magnetic field will be relatively weaker compared to if there are 3 or 4 lines are passing. So more number of line passing through an area, more is the magnetic field at that point. Now, magnetic field lines do not intersect, same as electric field lines, they do not intersect. For if they did, the direction of the magnetic field would be unique and would not be unique at that point of intersection. So as I said, so if suppose there is a magnetic field lines here, suppose there is another magnetic field lines here, at this point magnetic field lines will be either in this direction or magnetic field will be in this direction. But magnetic field magnetic field is a vector quantity and it has only one direction at a point, so it is not an unique direction. So we can say simply that this is not possible, this is not possible, this is incorrect. So we will just simply remove it. Okay, they cannot intersect at one point because of the it will lose the uniqueness of the direction of magnetic field. Now let's move on. Now we are talking about bar magnet as a equivalent solenoid. Okay, so basically what we are talking here, we are talking about a solenoid. Okay, and we are trying to find a magnetic field at a distance on the axis of the solenoid. Okay, now if you see that the magnetic field due to the solenoid is given by B equals to mu naught by 4 pi 2m by r cube. Okay, and vectorially you can write this like this. Okay, so it is on the axis, there is a perpendicular bisector as well, this is on the axis. Okay, and B on the perpendicular bisector or equatorial plane, let's say equatorial plane to keep it in same sign as electric field. The magnetic field is given by mu naught by 4 pi m vector divided by r cube. If you remember, this is the same as for electric field, similar to that of electric field. What was the difference between electric field and magnetic field? We will compare that also. Here this term m is called magnetic dipole moment, and magnetic dipole moment is basically pole strength of a single magnet. Suppose this is north pole. Okay, suppose this is north pole and the other one is south pole. North pole, south pole. Okay, now what happens is that there is a similar to that of positive charge, negative charge, there is something called pole strength. Okay, pole strength is generally represented by small m. Okay, so pole strength times the distance between the magnets. Pole strength times, suppose the distance is given here is 2L, so m times 2L is the magnetic moment. Okay, same as electric dipole. Okay, there is no basic difference between magnetic dipole and electric dipole, except that occurs in magnetism, this occurs in magnetism, that occurs in electric field. Okay, the formulas are same. Okay, only thing is this constant term is different. Okay, compared to that of electric field and magnetic field, this constant term is different, otherwise you can say they are almost equal. Now if we keep one small magnetic needle, okay, inside a magnetic field, same as electric dipole. Okay, electric dipole kept in an electric field, here magnetic dipole or magnetic needle kept in an external magnetic field. Now if you rotate, if this field rotates this needle to align it to some direction, then what is the, first of all, what is the torque acting on this needle? Torque acting on this same as electric dipole, capital M cross capital P. If you remember, in electric dipole that was capital P cross small p cross capital E. Here it is M cross B. Here M is same as magnetic dipole moment. Now when it is getting rotated, okay, to some angle theta, and the magnetic field itself is rotating this needle, so that the energy is stored as a potential energy. That potential energy is given by minus m dot b. Okay, p dot e, pe cos theta, same as m dot b. Now in this case the negative sign appears because the magnetic field itself is doing work. We are not doing any work. To rotate it back to its initial position, then we have to do some external work, so that work done will be positive, but this work is done by the system and this energy is being stored as a potential energy, so that's why this sign is negative. Okay, otherwise there is no change. Now let's see MCQ. A bar magnet of magnetic moment m is cut along its length into two equal parts. Then what will be the change in the magnetic moment of the magnet? So what is the meaning of that? Suppose I have a magnet north south. Now I have cut it along its length. Along its length means this is the along length. Okay, this is along width or along breadth. Okay, so it is cut into two equal halves along its length. Now now we have two magnets, one this, another one this. Now what is the magnetic moment of each of the magnets? So initially the magnetic monopole strength was m. Okay, now what will be the magnetic monopole strength? What do you think if we cut it into half? So in this case the magnetic monopole strength will be just half, right? Total strength should remain constant, similar to that of charges. You can compare that. Now length is remain constant, so 2L is the length in both cases. So what is the magnetic moment now? Initially the magnetic moment was m cross 2L or m2L. Okay, now the magnetic moment is m by 2 times 2L, that is ml, that is m by 2. So each of them will have a magnetic moment, m by 2 here, magnetic dipole moment, right? So m by 2 is the correct answer. Correct answer is option number C. Very common question. Okay, now let's move on. Now we are talking about the comparison between electric field and magnetic field. Okay, electrostatics and magnetism. So dipole moment. First of all, in electrostatic the constant was 1 by epsilon naught. If you remember, in electrostatic the constant was 1 by epsilon naught. Okay, in magnetism it is mu naught. Okay, or in other terms you can write this is 4 pi by epsilon naught. Oh, sorry, it is not 4 pi by epsilon naught, it is 1 by 4 pi epsilon naught. In this case it is mu naught by 4 pi, right? So 4 pi was, both of them were in denominator, so we are only saying 1 by epsilon naught, and here it is mu naught. Okay, dipole moment was small p, here it is capital M. Don't use small m. Small m is generally used for magnetic moment. Okay, similarly here if you see equatorial plane, it is minus p, it is minus mu naught m by 4 pi r cube. Okay, and on the axial field it is 2p 4 pi epsilon naught, this 2m, okay, 4 pi r cube. Okay, external field torque is p cross e, here m cross p. Okay, and in external field energy was p dot e, and here the energy is minus m dot b. Okay, if you consider negative sign generally do not consider in electric field, because in that case most of the time we are doing the work, but if the field is doing work, both of them will be negative. Okay, the figure shows a small magnetized needle placed at point O. So small magnetized needle is placed at point O. The arrow shows the direction of the magnetic dipole moment. Okay, the other arrow shows different positions and orientations of the magnetic moment of another identical dipole, another identical magnetized needle Q. Okay, so this is the main starting position of P. This is fixed, and you take another dipole, another magnetized needle, and you place them like this. Okay, now they have asked you in which configuration the system is not in equilibrium. You have to be careful. So to be able to achieve equilibrium, we know that the system has to have the minimum amount of potential energy. So potential energy, we know that minus m dot b, right? Minus m dot b. Now first needle is providing this b. First needle is providing this B, and second needle we are checking if the second needle will stay in equilibrium or not. So that is our point of concern. Right, now if you remember that in case of a dipole, remember the dipole case, electric dipole. Okay, there was a charge positive negative. Okay, dipole moment was from negative to positive, and if you put a charge here, the electric field was from negative to positive in this case, and if you put a charge here, it is in this direction, opposite to that of the dipole moment, right? Similar to that, if you put one dipole like this, okay, along the axis of the dipole, at any point the dipole moment in this case will point here, in this case it will point here, okay, and along the perpendicular bisector it will point either in this direction, or in this case it will be pointing in this direction. To find the equilibrium, we need to calculate the torque on the system, not the energy of the system. We need to calculate the torque acting on the system. So torque will be m cross b. If the torque acting on the system is 0, then we can say the system is in equilibrium. If the torque acting on the system is not 0, then the system is not in equilibrium. Okay, so basically this means mb sin theta. Now theta, if the theta is 0 or theta is 180 degree, torque acting on this will be 0. If the theta is 90 degree, torque acting on it will not be 0. So in this case we can see that for this dipole, okay, they are in the same direction, so theta should be 0. And in this direction, in this case they are in opposite direction, so basically theta is 180 degrees. So in this case also torque is 0. Here also torque will be 0 because 180 degree. In this case torque will be 0 because theta is 0 degree, right? But in these two cases, if you see theta is 90 degree, theta is 90 degree. That means these 2 points are not in equilibrium. So PQ1 and PQ2 are not in equilibrium. So the correct answer is option A in this question. Very interesting, important question, a different type of question. Okay, be prepared for such questions from this chapter, because some part which used to come in from this chapter is now deleted. Again I am saying this is also one of the chapters where most important common questions that used to come from this chapter, those are deleted. Okay, so these new concepts, new topics will be included in the upcoming KCET test. So if you are not prepared, then you are doomed. Now, magnetism and Gauss's law. Let's look into the magnetism of Gauss's law. First of all, the net magnetic flux through any closed surface is 0. So what is the meaning of that? Suppose, remember the electric field lines where we used to draw a sphere, and we say if there is a charge q here, okay, and whatever electric flux is coming out, E dot ds integral is equal to q enclosed divided by epsilon naught. But in case of magnetic field, this is 0. What is the meaning of that? So meaning of that, whatever electric field lines is going out, same number of electric field lines is coming in. Why so? First of all, this has two information. So two information, what are those two information? Whatever electric field lines is going out, that is sometimes after some time it is coming back. Okay, it is coming back. Also one more thing is why they are coming back, because there is no magnetic monopole. So there is no magnetic monopole means m, there if there is a plus m, plus small m, there will be a minus small m. Okay, if there is a plus small m, there will be always a minus small m. So total magnetic charge, you can consider this as a magnetic charge. So magnetic charge inside any closed surface will be always 0. Okay, so basically this is a direct consequence of magnetic field lines are closed and no magnetic monopole can exist. So these are the two things. That is the direct consequence of Gauss's law of magnetism. So magnetism of Gauss's law, it indirectly tells you that magnetic field lines are closed. Also indirectly it tells you that magnetic monopole cannot exist. Now let's look into another problem. Which of the field pattern given below is valid electric field as well as valid for electric field as well as magnetic field? Now if you see, this is valid for electric field, because if you consider this is a positive, okay, if you consider this is a positive, then obviously this is going out, valid for positive. But magnetic monopole, magnetic north pole, only single north pole is not existent, so this is basically incorrect. Okay, similarly if you consider this is a negative charge, this is valid for electric charges but not valid for magnetic fields. Okay, now if you consider this is valid for electric field. Okay, electric field can be, suppose here I have a north pole, here I have a south pole, then this is valid. But we do not see such kind of structures for electric charges, right? Electric charges, we do not see this kind of electric field lines. But this, if you see, what is this? This is similar to that of a bar magnet. Okay, and these lines can go out and come back somewhere, and same things can be observed for a dipole, right? So this is the correct option. This is the correct answer. This is from one of your previous year questions, so this is also somewhat important. Okay, now let's look into today's homework. Homework questions are relatively easy today because we are not doing very hardcore topic today. So check this homework problem, try to answer them, mention the answer in the comment below, mention homework number 1, answer is whatever it is, option A, option B, option C. Pause the video, check the question. Also the PDF of today's lecture will be available in the comment below, so you can download it from there. Next, homework number 2, this is little bit tricky but not very difficult. You can answer this question and mention the answer in the comment below. I will personally reply if you are answering correctly or incorrectly. Okay, done. Pause the video, check the question, write down the answer and mention the answer in the comment below. Okay, so we have reached to today's end of the today's lecture. So if you are having difficulty to get through all the videos, there is a dedicated playlist available for all of our lectures. For chemistry series there is a chemistry lecture series, for physics there is a physics lecture series. For all the subjects there is separate individual playlists are available. You can see all the videos in there. Okay, whenever you want you can revise it from there. So bookmark this playlist on your web browser or whatever, from wherever you are watching it. And please don't forget to join our WhatsApp group, and if you like this video don't forget to share it with your friends and subscribe to our channel. Thank you for watching.